Chapter 6 covers sort of a grab bag of topics, all concerned with how various parts of or various hardware subsystems within a computer system communicate and the performance issues associated with that communication as well as other performance issues associated with computer hardware. In this video, we're basically going to cover the first dozen or so slides associated with Chapter 6, which are all concerned with various aspects of the system bus and other buses in the computer system. Okay, so what is a bus? A bus is a shared channel that connects two or more devices. That channel could be electrical, it could be optical. In today's computers, it's usually electrical, but we expect optical channels to supplant those electrical channels at some point in the not too distant future. We generally think of that as a communication pathway that allows various parts of the computer system to talk to one another. And those various parts, as we've discussed in earlier chapters, the CPU, obviously a very important one, primary storage, memory, RAM, DIMMs, whatever you want to think of it as, secondary storage, hard disks, CD-ROMs, DVD-ROMs, solid-state disk drives, for example, and usually a grab bag of I/O units, things like network cards, things like the video controller and its attached display, the keyboard, the mouse, devices that might be attached by, say, a USB connection. Okay. All of these devices share a common communication pathway called the system bus. There may be other communication pathways in the computer system, but the system bus is kind of the central one that connects everything. Now, there are subsets of the system bus, but before we get to those, it's actually useful to kind of paint a picture. And there is a figure a little later in the book, and I forget exactly what its number is, but I'm going to pull up here the, where do I have it? Oh, there it is. There's a figure that's based on this picture. This is a picture of an actual PC motherboard, although at this point this is a relatively old motherboard. I don't remember exactly what vintage this board is. I think it's something on the order of 2008 or 2009. And there's a number of ways you can tell this is an older board. One is this green slot here is what's called an AGP graphics slot, which is kind of outdated at this point. It's been replaced by newer PC Express slots for graphic cards. The other way to know you've got an older machine is you've got is basically the shape of this socket here, which is this is probably a late generation Pentium or the very earliest generation of Core, but Intel Core processors, but I believe it's the latest generation of Pentium. Another way to tell this is old is you've got a number of older style secondary storage connectors here for what are called IDE hard disks. The newer connectors are these smaller ones on the right, which are for SATA disks. This board kind of represents a transition from one generation of PC design to another, and in order to increase flexibility, they've kind of overloaded it with both older and newer style ports. Okay. But my purpose in bringing this up is to kind of paint a picture of what a bus looks like. Now, one thing, it's a little difficult to see in here, but there is actually a communication channel, or a set of lines, which connect this slot here, and having trouble seeing that, to this slot, to these four white slots on the right, this AGP slot, this helper chipset for the CPU slot, the four memory DIMM slots, and various other ports here, or other connectors here for the secondary storage here along the top, and for various external devices here on the bottom. What I'm going to do, however, is I'm going to blow this up a bit so that we can get a better peek at this communication channel. Actually, I don't want to go to 200. Now, and the place I want you to look in particular is this area right between the CPU slot here on the lower left, the two of the memory slots here on the upper right, and then off to the right but kind of scrolled off screen, these expansion card slots and the video card slot. And if you look very closely here, you'll see a number of kind of light colored lines running, kind of northwest to southeast along this board. Okay. And note they're all lined up in parallel here. There's 1, 2, 3, 4, 5, quite a few of them here. Actually, let me get a pencil tool here for a minute. And let's see. Okay, so the area I'm talking about is right in here. Okay, see all these lines? There's one, and there's one, and there's one, and there's one, but my pencil's actually too wide. You see a whole bunch of them together. Okay, these communication lines connect the CPU to these slots up here. They run further over here and connect these to these slots on the right. Okay, although you can't really see them that well because this kind of the board is dark, but those lines run underneath the board here to connect these various slots on the right. They also run up here to connect these newer style SATA disconnectors as well as these older style IDE connectors, and they also run down to the bottom through some of these chipsets here and some of these capacitors to buffer the electrical signals from the outside world to these connectors here on the bottom, such as that one and that one and that one and that one, and I'm not sure exactly what all these are. I believe this one is a set of USB connectors. This is probably the external Ethernet port. One of these probably is an old style PS2 keyboard connector, and the other one is probably an old style mouse connector, and this really antique over here in pink is probably an old style parallel printer port connector. Okay, so as I said, this board is a definite mixture of old and new. But the point I want to draw at here is towards the center. These parallel lines that they're called traces. They're built. They're in the board itself, and they are the connection point. They are the physical embodiment of the system bus in this board. Okay. So back to this slide, system bus subsets. We can subdivide that set of connecting lines by function, okay? And it may be that we can actually point and say, okay, well, whoops, didn't mean to minimize that completely. It may be that we can say, okay, well, that part there is the address part, and that part there is the data part, and so on and so forth. Or it may be that some of these lines are shared amongst these functions, okay? But in terms of function, we can think of at least 4 categories of these lines, okay? Category 1. CPU, obviously, the CPU obviously is tied very closely to memory. That's where all the instructions are loaded from. That's where all the data is loaded from. That's where data outputs are first written to. Eventually stuff goes past there out to wherever, the video screen, the disk drive, the network card, what have you. But memory is sort of the hub of I/O activity between the CPU and everything else. And of course, memory is a whole series of locations, each of which has an address. So if I'm going to do a transfer from one place to another, and if memory is the one place or the other, then I need to know where in memory the data that's being moved is either going to be grabbed from or written to. The purpose of the address bus is to carry the address of either the source or the destination of that. The data bus, on the other hand, as its name implies, carries the actual bits of data. Okay, so, the mouse clicks, the keystrokes, the incoming network packet, the sector of data just read from a file on disk, whatever that may be. Okay, the job of the data bus is to carry those signals. Definitely in modern PCs, and actually most modern computers, we actually don't have physically separate data and address buses. We use one bus to carry both, either carry them both at the same time in parallel or carry them one after another. We might send the address first and then send the data in subsequent transfers afterward. Okay, the control bus. Well, obviously, in order to make this complex dance of bits moving back and forth across all these various components work, we need some control signals. Okay, we need things like, was the transfer successful? Who wants to talk next? Who wants to send data? How much data do they want to send? Is the recipient ready to receive it, or do we want the sender to wait until the recipient sends a command, says, okay, I'm ready? Okay, so there can be a whole set of signals, okay, associated with coordinating the movement of data back and forth across this bus, and the set of communication lines, or the portion of the bus that's used to carry those signals, is generically called the control bus. Okay, last is the actual power bus. Okay, on this particular, let me blow this up again. On this particular motherboard, we have one power connector, which is right here. So there'd be an external power supply that would feed power into this system through this connector. Various voltages would come in there, but subsets of these lines would carry that electrical power throughout the system. Okay, and would basically make all of the attached devices and all these chips on this system, on this motherboard, work. Okay, so a portion of the bus has to be dedicated to carrying power, or there has to be a separate bus that routes electrical power amongst all the various devices that are attached to the system. Okay, and typically we're going to support multiple voltages on there, because things like disk drives need a lot of power and tend to operate at higher voltages, whereas things like CPUs run at a much lower voltage, because the higher power, the higher voltages that would, are needed to, say, turn a motor in a DVD drive would overwhelm a modern CPU. All right, in the personal computer world, and this really extends into workstations as well, and really into mid-range computers, we tend to operate on standards that can be applied across multiple systems, and a standard that's been with us for quite a while in many different forms is something called the PCI standard, okay, which stands for Peripheral Component Interface. Okay. And virtually every PC today, as I said, and most workstations and mid-range computers use some variant of this PCI standard. It's been around with us, I don't know, a couple of decades, I believe, at this point. In common use, it was probably under development before that. And it's been through quite a few variations and changes over time. Okay. One big break from old to new is something that we'll cover more in Chapter 8, okay? And it's the issue of parallel channels versus serial channels, okay? In a parallel channel, we have one electrical connection per bit, okay? One electrical connection per bit. So if, say, we have a bus that's going to allow 32 bits of data to be transferred at a time from, say, memory to the CPU or from an external device, we're going to have at least 32 electrical connections, okay, dedicated to carrying data, one per bit. Okay. And of course, if it's 64, well, then we've got 64 connections. Okay. Looking once again at this motherboard example we have here, and the data lines I have, you would probably guess that this is a parallel bus, and you would guess correctly by the number of data lines that are running in parallel here. As once again, we'd really have to blow this up quite a bit to see that detail, but there are a lot of data lines running right next to each other. Okay, so this is almost certainly running an earlier PCI bus standard based on parallel connections. Okay. The more modern approach to this is what's called a serial data channel. Okay, and in a serial data channel, we don't have one connection per bit. Instead, what we do is we use one or maybe a pair of electrical connections to carry data, and we send bits one at a time down those serial data channels, and hopefully we can send them much faster than we can with a parallel connection. Otherwise, the parallel connection would have a big advantage in terms of data transfer rate. Okay. So on the earlier PCI versions, yes, we have one electrical connection, or one wire, if you like to think of it that way, per bit. The address and the data bus lines are shared. Okay, we send the address, then we send the data. The problem with parallel channels is they're relatively slow. Okay, they're relatively slow because of things that we'll cover more in Chapter 8, but the basic issue is skew. Bits arriving slightly out of time with one another. Okay. Another limitation of a parallel channel is that all of the attached devices have to operate at the same clock speed. Okay. And kind of think of this in terms of chain as strong as its weakest link. Basically, the slowest device in the system determines how fast the system runs, and as you might imagine, that could be a rather significant performance impairment if there are slow devices in the system. Correspondingly, if you want the system bus to run very quickly, then all of the attached devices have to run quickly, which makes them much more expensive. Okay. With PCI versions, you have far fewer electrical wires because now you can, send bits serially down one wire, one right after the other. Okay, and what you get is the connectors and the bus itself and cables, if there are cables, are physically much smaller. And actually, probably the best visual example of this is right on this motherboard here. Okay, here on are two connectors for a modern SATA serial. This is a serial cable connection for a modern disk drive, or at least more modern than the ones to the left. Okay, and you'll note there's 1, 2, 3, 4, 5, 6, 7 wires that constitute this. Only 2 of those are carrying data. Okay, so this physical connector and the cable that would be attached to it is significantly smaller than this one just to the left of it here, where I believe if you count those up there are 49 connections. Okay, 32 of them dedicated to data and the rest dedicated to a few other things. So just looking visually at the two on the right versus this one on the left, I mean, you could fit roughly 3 of these connections in the space occupied by one of these. Okay, and of course, if we were looking at cables, this would be a very large, bulky cable, whereas this would be a much smaller cable. Okay, so the serial connectors are physically smaller because they have fewer wires. The cables are smaller. The number of quote-unquote wires that need to run through this motherboard to attach these to the system bus and to other devices is fewer and therefore smaller. For the reasons we'll cover in more detail in Chapter 8, the serial can generally also operate at a higher speed. Okay. And in addition, it doesn't require all of the devices to operate at the same clock speed. Okay, so fast devices can use whatever expensive circuitry is necessary to operate at that high speed, but slower devices can operate at some fraction of the maximum speed and can be therefore implemented with cheaper devices. Okay, so for a lot of reasons, serial data channels have basically taken over in the bus world. Universal Serial Bus, for example, for external connections, and the latest PCI versions, such as PCI Express, using serial connections. And then in addition, for example, SATA, as opposed to the older IDE standard, serial versus parallel, for connecting disk drives and other secondary storage devices. Okay, so let's move on and talk about clock rate. Okay, like the CPU, bus has a clock rate. Okay, think of it this way. Okay, let me back up here to the picture again. Okay. For some period of time, well, let's say a device attached to this board here, okay, wants to send data to memory, and in particular we're going to send data to this memory chip, or the DIMM, that's stored in this slot right here. Okay, that means that electrical data has to go from here to here. Okay, and we don't have a scale on this, but if I remember this motherboard correctly, this distance is probably about 4 inches. Okay, the distance from this slot to here is about 4 inches. Okay, so electrical signals, in this case 32 parallel electrical signals, have to go from this bus, or this slot, to this slot. Okay, now what does that have to do with clock rate? Well, think of a single transfer of 32 bits. Okay, whatever the device inserted into this slot is, it's going to energize those 32 data lines with whatever voltage this system carries. It's probably carrying 5 volts. Okay, and those 5 volts have to travel from here to here. Well, electricity takes time to travel, although it's moving at, near the speed of light, so that travel is going to go pretty quickly. Although the longer the distance it has to travel, the electricity is going to take to get from point A to point B. Okay, so this device is going to put voltage into those 32 lines representing the zeros and ones. Okay, it's going to continue to put that voltage in for a certain amount of time, and then it's going to stop. And then as far as this device is concerned, that ends one transfer of 32 bits of data. If there's more data to come, then it's going to grab the next 32 bits and it's going to put those onto the electrical lines. Okay, so there's a period of time during which one set of 32 bits is on the line, then there's another period of time which the next set of 32 bits on the line, and so on and so forth. Each of those time slices is a clock slice. Okay, it's one bus cycle. Okay, and the clock rate is simply the number of, the cycle time is simply 1 over the bus clock rate. Okay, so there's just an inverse relationship between the two. So for example, if the bus operates at say 1 gigahertz, then a given set of data will be present on those electrical communication lines for 1/1000th of a second. Okay, and in theory we can do 1 billion transfers, each one being exactly 1/1000th of a second apart. Okay, so that's the basic idea of clock rate, and it's really not any different from the concept of clock rate we discussed back in the chapter on CPUs. So now let's talk about back to the parallel versus serial bus. Okay, for the older style parallel bus standards, you've got a relatively slow clock rate compared to today's. Okay, I believe the PCI-X standard, which is what preceded the first serial version of PCI, maxed out at 66 megahertz. Maybe they took it to 100, I don't remember, but I think 66 is where they maxed out. They really couldn't push it any faster than that, and to do so, if they had tried, they would have either run into a lot of errors and required a complicated error correction strategy, or they would have had to have very expensive peripheral devices, and the cost of that motherboard we looked at would have been, triple, quadruple what it actually is. Okay, so 66 is pretty much where it maxed out. For the newer serial buses, the current PCIe standard clocks at 2.5 gigahertz. Okay, note that's a pretty big difference from 66 megahertz. Okay, we're up, 2 zeros, 2 orders of magnitude. Okay, now the difference is that PCI-X standard operating at 66 megahertz, depending on which kind of, what specific version you were using, was either transferring 32 bits per clock cycle or 64 bits per clock cycle. Whereas in PCI, you're transmitting 1 bit per clock cycle. Okay, or if we use a variation of the PCI, which I'll talk about in a minute, maybe you can get a few bits per clock cycle. Okay. So what happens during that clock cycle? Well, the sender activates, those lines, puts voltage into them, representing either data or an address or a command, and that voltage is there for 1 cycle. The receiver has 1 cycle to see that voltage, recognize it as a message, and quote-unquote read its contents. Okay, and typically the receiver is going to transfer it somewhere into an internal buffer, or in the case of memory, it's just going to store it in the DIMM chips. In the case of a CPU, it's probably going to stuff it into a cache or stuff it into a register. Okay, so this clock it's basically what keeps everybody operating on the same wavelength, so to speak. Okay, all the devices in the system use the same clock to coordinate this flow of data back and forth. Okay. Now, we've kind of discussed this issue of length. The system bus has to be relatively long because it connects all of the devices in the system. Okay, back to this motherboard. Let me shrink it down here a bit. Okay, doesn't look like much in this picture, but the whole length of this was probably about 8 or 9 inches, and it's probably about 7 inches up and down, 7 or 8 inches up and down. That doesn't sound like much, but in the world of electricity, moving at gigahertz speeds, 8 inches is a long way to go. Okay. think of how much shorter the connections are between, say, chips in your cell phone. Okay, so, but computer system, you've got disk drives attached, you've got DIMMs, you've got CPU, you've got all these external connectors down here at the bottom, you've got a video card here with a monitor attached, maybe you've got some graphic cards. It's just the nature of a computer system that because it's got a lot of attached devices, the bus that connects those devices has to be relatively long. Yes, we'd like to miniaturize it as much as possible. Maybe we can get it down to a few inches, but we're still on the scale of inches, not on the scale of, micrometers or nanometers or the kind of scale that, say, occurs within the CPU. Okay? So that long length is a long distance for the electricity to travel. The speed of the electricity is constant. So basically, as the length goes up, the clock rate goes down. Or I'm sorry, the clock rate goes down, yes, assuming all other things are equal. Okay. So given the same bus specification, parallel or serial, as I stretch out the maximum length of the bus, the clock rate has to go down to compensate. Okay. Correspondingly, if I want to increase clock rate, well then I got to put things closer together. I got to shrink the maximum length that electricity has to travel from the sender and receiver on this bus that are furthest apart. Okay. So the length determines the theoretical maximum clock rate. Okay. However, the actual clock rate is usually less than would be determined by the length. Okay. And there's several reasons for that. One is as you increase speed, you increase error. And typically inside computers, errors are things we want to avoid. Okay, so we set the rate a lot lower than the theoretical maximum so that we can keep the errors down, hopefully to zero. Okay, another issue. If you want to make something very fast and error-free, guess what? It's going to be more expensive. Okay, and people wouldn't be happy if, say, USB ports were $100 a piece and USB cables were $75 a piece, and so on and so forth. One way to keep the cost down is to keep the speed down. Okay, this is probably not true anymore, at least not on serial channels. Bus is a chain only as fast as its slowest device. As we said earlier, one of the advantages of going with a serial bus standard is that that's not true anymore. Okay, basically what it boils down to, it's a cost-performance trade-off. Okay, the closer you push to the maximum, the more attention you have to pay to avoiding errors, either by building very expensive interface devices or building some sort of error detection and correction into the bus protocol. Okay, so let's take a look at some transfer rates here. Okay, data transfer rate for a bus is computed the same way it is for any other device. Basically, only have two input variables. One is the clock rate. Okay, how many data transfers occur per second or per time interval, and the other is how much data are you moving per transfer. Okay, so what's the unit size, how many bits of data at a time, and how many transfers per second. So for an older parallel bus, okay, you've typically got a slow clock rate. 66 megahertz was the max for PCIX, as we discussed, but you've got a fairly wide data path, typically 32 or 64 bits. So let's say you had one of those latest and greatest PC workstations or PCs based on the PCIX standard, and you had a 66 megahertz bus that was 64 bits wide. Okay, 64 bits, 8 bits per byte, that works out to 8 bytes times 66 million. Okay, that works out to about 528, well, exactly 528 megabytes per second. Okay, clearly that's sub-gigabyte level, but that's reasonably impressive. Okay, that's certainly much faster than any single disk drive in the system. Okay, it's probably fast enough to support a graphics interface as long as it's not too high a resolution. Okay, although it is considerably slower than the CPU can do transfers, say, internally from registers to ALU or what have you. Okay, for one of these newer serial buses, say PCIe, you got a fairly high clock rate, 2.5 gigahertz is the standard, but your data transfer unit size is low. Okay, so let's assume for the moment you're only transferring 1 bit. Okay, 1 bit times 2.5 billion, okay, is 2.5 billion bits per second, or to put it in bytes, that's 312.5 megabytes per second. Okay. So, looking at this, okay, 312.5 versus 528, you might say, well, hold it, we went to serial bus because it was supposed to be better, but it's actually slower than the old parallel bus. Okay, well, that's true, but there are things we can do to improve that. Okay, so looking at this basic formula, how do you increase data transfer rate? Well, there's basically two ways to increase data transfer rate. You can either make clock rate faster, or you can make data transfer unit size larger. Okay. Another thing you can do, although we haven't really discussed bus protocols at this point, is you can use a more efficient bus protocol. Okay. You can ensure that everything you're transferring is actual useful data, as opposed to control signals or error detection and correction bits or other things, non-data things that you might transfer across this bus. Okay. All right, what I'm going to do now is take a little side tour for a minute into some of the PCI specs to kind of put some meat behind a few of these issues. Back a few slides where we talked about PCI. There was a couple of links in here, and the link I'm looking at right now is this one, Design PCI Express 1X pinout. Okay, so we're looking at the PCI Express 1X slot standard. Okay, and there's a connector that slips into a slot, okay, much like the motherboard we looked at, okay, and that connector has electrical contacts on both sides. So there's a side A and a side B. Each side has 18 connections, okay, but since there's two of them, there's actually 36 connections in total. Okay, and also we can roughly divide these into two subsets. Okay, from 1 to 11, we can pretty much think of all of this as the control bus. Okay, and from 12 to 18, we can pretty much think of this as the data bus. Now, in fact, both halves of this also have power routed through them. Okay, so let's back up for a minute to some of these earlier slides and hit some of these concepts. Okay, so address bus and data bus, as we said, they're actually both carried on the same bus nowadays. Okay, and if we're looking for the address/data bus, we're going to find it right here and right here. And you'll notice we have a transmitter lane, which corresponds to 2 electrical contacts. Okay, and we also have a receiver lane, which corresponds to 2 electrical contacts. Okay. The modern PCI standard encodes data bits using 2 pairs of electrical contacts using something called low voltage differential signaling. And we don't need to get into the details of that. Simply say that by using that method across a pair of wires at the same time, you can operate at a much higher clock rate and not have to worry too much about errors. Okay, you can get error-free data transmission of single bits across a pair of connections using LVD or low voltage differential encoding with an acceptably low error rate, meaning virtually none. Okay, so these, and we've got 2 of these. One, and the one thing that distinguishes the PCIe from its earlier predecessor is, in its earlier predecessor, data moved one direction or another, but it couldn't move both at the same time. Okay, in the PCIe standard, you have 2 different pairs of data transmitters, so basically 2 devices can be exchanging data in both directions at the same time. There are situations where that comes in very handy, although we don't need to talk about them right now. Okay, as I said, we can think of the upper half of this set of connections as the control bus. You'll see there's a clock signal. Okay, so that's ticks coming 2.5, to 2.5 billion times per second. Okay, this is not the actual data bus. Okay, we talked about the power bus, and we see there's plus 12 volts. Okay, coming across these two connections. And across these two connections, there's 3.3 volts of power coming across these connections and this one. And there's also a lot of grounds. These are the return. Remember, every electrical, if we send electricity, there has to be a return wire to make a complete circuit. So there's a ground, there's a ground, there's a ground, there's a ground. We've got a lot of grounds spread around here. Basically, the more grounds, the more predictable the electricity is as it moves across these signals, and the lower the error rates. Okay, so typically in a bus, you've got somewhere on the order of 10-20% of the electrical lines operating as grounds. Okay, so this is how the PCI Express kind of lays out in terms of the various connectors. So think of this as, let's see if I can get them up side by side. And of course, we're talking about two different generations of bus standards here. But think of this table on the right, okay, as describing each contact pin on one of these white connectors down here on the lower right. Okay. Now, in fact, the connectors in a PCI Express motherboard would actually be a little smaller than these because there's fewer of these needed. But see each of these kind of vertical lines there. Think of that as one electrical contact. Okay, and these are the signals that travel across those contacts. One on the left, the side B would be on the left side of this, and side A would be on the right side of this. All right, let's see, moving forward here a bit. Bus clock rate, as we said, we're operating at 2.5 gigahertz. We already saw that implies a raw data transfer rate of 312, what was it, 312? Yes, 312 megabytes per second. Okay, now note that's 312 megabytes across this one, and 312 megabytes across this one. So if you do need to transfer data in both directions at the same time, effectively you're doubling this 312.5. So that's 600, so we're already above the PCIX. Okay, data transfer rate. Now let's look at one more game we play. Okay, what we're looking at is the pinouts for what is called the PCI Express 1X, meaning there's one pair of data transmission. Okay, there's also a 4X connector with 4 pairs of data, or think 4 bits at a time in both directions. An 8X connector, okay, 8 bits at a time in both directions if you want. A 16X connector, okay, 16 bits at a time. So it almost sounds like we're going back to the parallel standard, the parallel days here. And there is actually also a 32-bit, 32X bus width, okay. And this, these 16 and 32s, these are what are commonly used for video cards. Okay, because video cards need that kind of throughput. Okay, whereas most of the other devices can operate lower. Say a disk drive, for example, might operate in the 8 or 16 range. Something like a USB port, a 4X would probably be fine. A very slow device like a keyboard or what have you, clearly the 1X is more than enough. Okay, so the way we get additional capacity out of here is really by kind of being both serial and parallel at the same time, rather than just having, this 312.5 is the rate of one channel and 1 bit per channel in one direction. Okay, as we've already seen, we can go in both directions at the same time, so we can double that. And then, of course, we can add multiple of these bit channels on a side-by-side basis and multiply this again. So it's not unusual to see PCI transfer rates well into the gigabytes per second simply by using these quote-unquote wider slots. 2x, 4x, 8x, 12x, 16x, 32x. Now you might say, well, hold it. As soon as we start carrying 2 or 4 or 8 or 16, aren't we going to run into exactly the same problems we ran into with the old parallel buses? And the answer is no, because they're really not operating in parallel. Each of these channels, quote unquote, at least in the electrical sense, operates independently. And once again, we need to get to Chapter 8, and we're not there yet to really discuss this issue in more detail. But suffice it to say, even though it looks like we're doing parallel when we use, say, one of these 32x slots, what we're really doing is running 32 independent single-bit channels. Okay, and that independence allows us to avoid many of the problems associated with the older parallel bus standards. Okay, so the bottom line is bus data transfer rate, while it looks pretty small, measured one channel, one direction, or one bit at a time, one direction, actually can get pretty large by bidirectional data transfer and larger bus widths, larger numbers of bits carried at a time. Okay. Let's see, did I catch everything else I wanted to do? Okay. Bus protocols. Okay, so the bus protocol is, we call it the language of the bus, but it's really more than just a language. Okay. One aspect of the bus protocol is which lines are used for which purposes. So for example, this table here. Okay, we've got 18 times 2, we've got 36 lines on a 1x PCI Express bus connection. Okay, which lines are used for what? Which carry power, which carry ground, which carry clock, which carry data, so on and so forth. Okay. What are the electrical and optical characteristics of each signal? Okay, so for example, in this transmitter lane 0 differential pair, what's the voltage level? What's the resistance of the line? Okay, what are those electrical characteristics of the signal crossing that? That's part of the bus protocol. How are bit values encoded in a line? Do we use positive voltage for ones and negative voltage for zeros, or do we do something more complicated? LVD, or low voltage differential encoding, being an example of something more complicated. Okay. How are commands, errors, and status information encoded in bit values on the control bus? Okay. What's this clock signal look like? Okay. Is it simply a series of pulses coming at, say, 1 volt or 3 volts or 5 volts? Okay. What about these signals here? TCK, TDI, TDO, TMS. I'm not going to go into those, but what do they mean, and how do we interpret if electricity is coming across, say, the second and the fourth, but not the first and the third? What does that mean? Okay, what does that mean in terms of a command? Is that read, write? Is that an error an error code, a status information? What is it? Okay. Last issue, probably one of the more complicated. Which devices get to use the bus when? Okay, I mean, think of it as like when you're sitting in a classroom. Okay, can anybody in a classroom just start talking at any time? Well, if you allow that to happen, then typically you get a lot of noise, and there's not a lot of efficient communication going on. If it's a typical classroom where you've got an instructor sort of leading things, you've got a set of rules. You got to raise your hand, and when the instructor points at you, then you get to talk. Okay, so think of the air in the room as the bus. Okay, that's the shared communication channel between everybody who's sitting in the room. How do you ask for access to the air to communicate? Well, you raise your hand and you wait for the instructor to point to you. How long do you have access? Once the instructor points to you, can you just talk forever? Or, is there some time limit on this, after which you got to, give control back to the instructor or over to some other student? Okay. Put all this together and you've got a bus protocol. Okay. Now, different bus protocols vary in their efficiency. Okay. And for stepping aside for a minute, note that when we're talking about PCI Express, we are talking about a bus standard both in the electrical sense, electrical and optical characteristics, which lines for which purposes, and in the control, command, access status. Okay, so it's both rules for how you use it as well as lower level rules for how you encode it and send it electrically. Okay. So different bus protocols, say PCIe versus PCX, vary in their efficiency. Let's take some extreme examples here. Imagine we have a bus protocol in which we use one cycle to transmit a command, say read or write, and an address, and then in the next cycle we transfer one group of data bits. Okay. And then the cycle after that, we transfer another command, then after that, another set of data bits. Well, how much data can actually move across the bus? Well, if every piece of data has to be preceded by a command, in essence, half the cycles available bus cycles aren't being used to carry data. So backing up for a minute, even though in theory the data transfer rate, say we're dealing with this bus here, is 528 megabytes per second, with that one command then one data transfer sort of bus protocol, effectively we've cut this rate in half. Okay, because half of this capacity is being used to carry commands, the other half is being used to carry data. Okay. Oops. Okay. More efficient protocols, it's funny, it may seem it's actually somewhat counterintuitive, but more efficient protocols tend to be a little more complex. Okay, they require typically a more complex command structure and typically a larger number of control bus lines. Okay, they require more lines to carry data. Okay, be that older parallel 32 or 64 or newer serial independent serial channels running multiples of those. Okay, and basically the more complex the protocol, the more complex is the interface circuitry for devices that attach to it, and of course that makes things more expensive. Okay, good example here would be something like, say, SATA versus SAS for disk storage buses. Okay, SAS devices, that's SAS is SCSI, serial attached SCSI. Okay, and we'll talk about that, talk more in detail about that a little later. But that's a more complex bus protocol than SATA, and the devices, the disk drives that use it, tend to be more expensive. Now, is the additional expense entirely due to the complexity of the bus protocol? No, but it's part of the additional expense. Okay, let's come back to this issue of control. So who gets to talk when? You know, who kind of quote unquote directs traffic on the bus? Okay, well, there's two basic ways to approach this. Okay, one is called the master slave. Okay, you know, imagine you've got a policeman at an intersection where the traffic lights are out. Okay, and that policeman is essentially the master. You know, you sit there until he points at you and says you can move, and then you can drive through the intersection. If he holds up his hand, you stop. Okay. Nothing goes through that intersection that doesn't go by him at his explicit command or her explicit command. Okay, it's a classic example of master-slave. Okay, so the bus master in this case is the policeman standing in the intersection. Okay, in the bad old days of computer design, the CPU or some supporting chipset was the bus master. Okay, and it controlled all transfers across the bus. You know, disk drive wanted to move data to memory. It did so at the explicit request and with the explicit permission of the CPU. Okay, every other device attached is a slave. Okay, it has to wait for instructions. It has to ask permission before it can do anything. Okay. Advantage of this is it's simple. Disadvantage is it's relatively inefficient. Why? Because the bus master is a bottleneck. Okay. And particularly in the model world, the CPU's got much better things to do than be directing traffic. Okay. More modern approach is what's called a peer-to-peer bus. Okay. And in a peer-to-peer bus, at least in theory, we're all equal. Okay. So think of a classroom discussion with no instructor. Okay, how's it going to work? Well, any student can talk, can quote unquote be bus master, but you know, in order to ensure everybody's voice gets heard and, you know, an efficient flow of information, you're really going to need some sort of protocol for passing around the role of who gets to talk or who gets to control this. Okay, it may be a fairly simple protocol of raising hands or just nodding, or it may be unspoken, you know, but it needs to be there. Okay, and there also needs to be some sort of prioritization scheme for what happens when two devices want to communicate at the same time. You know, you can't send two different electrical signals across the same set of wires at the same time. Okay, if two people talk in the same room at the same time, their acoustic energy is going to interfere with each other, and the chances are nobody's going to be able to hear what either of them are saying. Okay, so in general, you want one message to transfer the bus at a time, and you need a prioritization scheme for determining who gets to talk first when two people want to talk at the same time. Okay, just as true of peripheral devices in a computer system attached to a system bus as it is of students in a classroom. Okay. Now, let's talk a bit about data transfer rate mismatches and the role of memory. Okay. Looking just at clock rates, you might say, well, hold it. My Intel Core is clocked at 2.4 gigahertz, and now I know that my PCI bus is clocked at 2.5 gigahertz. Aren't they both, the same speed, quote unquote? Well, yes, they're the same clock rate, but remember, your CPU is a 64-bit device. Okay. So that's 2.5 gigahertz times 64 bits per clock cycle. That's a pretty big data transfer rate. Okay. Whereas other devices, okay, attached, say, to a PCIe 1X slot, are operating at roughly 1/64th of that speed. Okay, so usually you're looking at a difference in data transfer rate, not clock rate, data transfer rate of 2 orders of magnitude or more. Okay, the fastest devices in the system, say the video card, might be only 1 order of magnitude slower than the CPU. Things like disk drives might be 2, 2.5, 3 orders of magnitude slower. Things like keyboards aren't, even in the same universe in terms of speed. Okay, even a gigabit network card is, several orders of magnitude slower than the CPU. Okay, so, and the bus. Okay, so the bottom line here is, particularly for slower devices, if you would to interface them directly to the CPU or to the system bus, you would waste either bus cycles or CPU cycles. Okay, so to improve performance of data moving to and from the CPU, we always move it through memory. And in the old days, we called this direct memory access. We don't use that term much anymore because that implied a very specific technology for how memory was wired to the bus and and a specific bus protocol for directing things back and forth. And that bus protocol is, from the 80s, so it's obviously pretty ancient. But thinking of it more generically, simply the fact that in order for data to get from any device to the CPU, it has to first move through memory, or through memory going in the other direction. Direct memory access is still with us, just not the same protocol we were using back in the 80s. Okay. And by moving everything through memory, what that allows the CPU to do is not be the bus master. Okay. It only takes the bus master role when it absolutely has to, which is generally never. Okay, looking back at this motherboard image once again. Okay, typically the role of bus master, is taken on by a supporting chipset. Okay, and in this case, I'm actually not sure which chip here it is. I'm thinking it's this one right there. Okay, although you can't see it because it's buried underneath of a heat sink and it's hardwired to the board. Okay, this is the supporting chipset that allows the CPU to talk to the PCI bus. Okay, but the CPU would rarely talk through this chip, say, to one of these slots on the right. What it does instead is talk through this chip to memory. Okay, all these other devices talk through this chip to memory, and CPU does all of its I/O directly to memory if possible. Okay, and that leaves all the other communication to occur across the system bus without the CPU's knowledge. It's like, okay, when the data is in memory and ready for me to read, you let me know, and then I'll go grab it directly from memory. And since I have a very high speed, I'm speaking as the CPU here, since I have a very high speed connection to memory, I'm not wasting my time speaking very slowly to the keyboard. The keyboard speaks very slowly to memory, and then once everything that comes from the keyboard is sitting in memory, now the CPU grabs it in a hurry. Okay, so the CPU gets to operate at its much higher clock rate, the slower devices get to operate at their slower speed, and the CPU doesn't spend a lot of time twiddling its thumbs waiting, in the infinite spaces, quote unquote, between words of a device that simply speaks too slowly for it. Okay, so that's the basic idea behind direct memory access. As I said, don't get carried away with this acronym. Okay, this means something very specific in an 80s era PC computer, but it's also a generic concept that survives to this day and probably well into the future. And that's the sense in which I'm using the term here. Okay. All right, we're coming up on an hour. I'm going to try to wrap this up by an hour here. Let's talk about multiple buses. Okay, so in the bad old days, although interestingly enough, bad old days have a way of coming back around. Okay, there was only the system to bus, and everything was attached to it. Okay, there was a relatively simple bus protocol. CPU played the role of traffic cop. Eventually, that got offloaded to a supporting chip, but basically, this was a relatively inefficient approach. Okay. And the reason primarily is it was a parallel bus, and that meant speed was limited by the slowest devices. Okay. Plus, the CPU was spending its time playing traffic cop, which meant it had less time to do its real work. In the modern world, we tend to go with a set of buses specialized to various purposes. And this has changed somewhat over time, and it's actually changing as we speak, but let's talk about the details and then we'll get to them. So we still have a system bus. There is still a PCIe bus that connects every device in the system. Okay. But there are some separate buses that allow traffic to quote unquote be routed around the PCI bus. By far the most important one from the point of view of performance is a separate bus connecting CPU to memory. Okay. So while disk drives are transferring data to one part of memory, the CPU can be pulling data from another part of memory, okay, or writing to that memory. Okay, so basically the CPU gets to talk to memory whenever it wants, and at a relatively high speed. It's a high clock rate bus because it's a fairly short distance. Okay, once again on this motherboard, note that the CPU and the DIMMs sit right next to each other. Okay, that's an intentional design. This is a short distance, and therefore you can do these transfers at a much higher rate. Okay, and it supports two-way communication, so you can the CPU literally can be reading and writing memory at the same time. Okay, in much the way the PCI bus can send two bits in two separate directions. Okay, now as shown on the motherboard we've been looking at, there may be a separate bus for the video. Okay, and back in the era of this motherboard, that was a necessity because remember, this motherboard has PCIX parallel bus 32-bit, which is a definite performance bottleneck for video. Okay, so the way this motherboard got around that performance bottleneck is it had a separate bus and a separate slot here just for video communication. Okay, this basically connected video to RAM, to memory. So there was a direct channel here as well. Okay, and that enabled lots of data to move from RAM to the video card in a hurry. Okay, while other transfers were taking place at other parts of the system. Now, roll the clock forward. Once PCIe came out and once these X16 and X32 data width PCIe cards became available, they provided the kind of bandwidth that was needed to support video, and the PCI standard is smart enough and efficient enough that it can handle those and other transfers at the same time. So what you've seen is this separate bus for video has pretty much disappeared from PCs. Okay, you can still find variants of it in some very specialized graphics workstations. Okay, but as far as common computer use, it's disappeared. Now, maybe it'll come back at some point. Maybe that basic approach will come back. But at the moment, this is not something you commonly see. However, this you definitely still commonly see. Okay, there are separate secondary storage buses. Okay, SCSI or SAS and SATA being two prime examples. Okay, back again to this motherboard image, if I can find it. Okay. Back up here to the upper right hand corner. These two slots, this up here on the right, okay, these two SATA connectors, they are part of a separate bus, okay. That bus eventually connects down here to the PCI controller, but that separate bus allows data to move between disk and memory independently of other transfers taking place. So as you see now, on this particular motherboard, we've got a separate bus connecting memory and the CPU. We've got a separate bus connecting the disk drives and the CPU, and we've got a separate bus connecting graphics port or video port and the CPU. Boy, memory better be fast if it's trying to handle transfers across all three of those at the same time. But note it's not just three, it's four, because we've still got the PCI system bus that connects everything. Okay. So in theory, 4 sets of data transfers can be taking place across this motherboard at the same time. And that's really what this approach to system buses is all about. Take groups of devices that have things in common, functions, speed, what have you, and segregate their communication out onto a separate channel so that it doesn't clog up the main channel. Do that wherever it makes sense. Clearly it makes sense between CPU and memory. It probably also makes sense between secondary storage and memory. Okay? Allow those channels to be customized to those purposes, be it speed, be it width, be it command structure, be it whatever, and provide those as subsidiaries to the main system bus, and that improves overall efficiency throughout the system. Okay, here's the motherboard picture we've been talking about, but of course now you've seen it, we've kind of gone all through it. Okay, and the last piece of this, there's an exercise. I'm not going to go through the whole thing, although I have done a little bit of expansion for my computer here, the one I'm doing this video on. Okay, so let's see here. Let's get this off on the right, and I'll just very quickly look at a couple pieces of it because we're at 1 hour and 44 seconds, and I don't want to go much longer. So on a Windows machine, right-click on My Computer, select Properties, select Device Manager, click on the View menu, select Devices by Connection, and you will be looking at this. Okay, and let me undo some of these. Okay, so View, Devices by Connection will give you this basic view. Okay, so my computer is called Aguila. Here are the primary devices attachment points. Okay, but as I start clicking some of these points, I see, okay, this is the PC connection, and note that I have connection points for the power button, the event timer, the 4 CPUs. This is actually one microprocessor with 4 cores. And then there's the PCI bus. And if I expand it, okay, there's a whole bunch of things attached to this PCI bus, roughly 2 dozen or so here. Okay, got an audio controller, got the gigabit Ethernet connection, got a bridge, quote unquote. Here's my SATA controller. That's my interface to secondary storage. Okay, I've got a whole bunch of USB attachment points. Okay, and a couple of other things that we don't need to get into. Let's take a look at the SATA. Okay. I have an array here. Okay, now I can't see the details of the array because they're hidden to me, but I actually have 2 disk drives running in a RAID array here, kind of ganged together for speed. We'll talk about that in a later chapter. Okay, and then if I start opening up some of these PCI devices, let's see what I've got connected. Let's see here. Okay, I have a OfficeJet printer attached to this hub to this particular connection. What's over here? My LifeChat LX, that's the headset that I'm talking into right now. Okay. Let's see what else here is. Oh, I've got some Bluetooth devices. Okay, my keyboard and my mouth are wireless, operating through Bluetooth. Okay. So as you can see here, the PCI bus really is what kind of, ties all this stuff together. Note that you're not really going to see the details of any of these other subsidiary buses. In particular, you're not going to see any details of the direct connection from the CPU to memory. Okay, but you do, for example, here's the subsidiary bus for the SATA disk drives, note that it is slave to the PCI bus. So if the SATA devices want to talk directly on my particular machine to memory, they've got to go through the PCI bus in order to do it. Okay. Although once again, remember, this is a newer, I'm doing this on a newer PC than the motherboard we've been looking at. So the bus running here is a PCIe bus, and most likely this interface card here is either a 4X or 8X card, so that it can have much higher throughput. All right. That concludes this video. So at this point you should have a pretty good idea of what a bus is all about, issues like parallel versus serial, bus standards, bus protocols, and the role that the role that multiple buses can play in improving the performance of the system overall.